Welcome to this explainer. I'm thrilled you're here. After 30 years of staring down materials as a materials scientist, I've realized most folks just think of degradation as, well, a bit of ugly rust on an old car. But believe me, what we're actually dealing with is a highly complex, microscopic, and honestly, surprisingly aggressive world of chemical warfare. Today, we're taking a forensic journey into the microscopic and laboratory techniques we use to measure, understand, and ultimately prevent this material degradation. So grab your safety goggles and let's see exactly how this enemy operates. Now, I want you to start by pondering a pretty stark question. What does it actually look like when a metal eats itself alive? We aren't just talking about cosmetic blemishes here. Corrosion is an existential, trillion-dollar structural threat to our global infrastructure. It's literally these silent attacks on everything we build, silently hollowing out the foundations of our modern world. To fight it, we scientists have to understand exactly how the enemy operates. All right, welcome to our very first crime scene. What you're witnessing here is severe surface degradation on a material after just 46 hours of extreme chemical exposure. Look at this specific environment we exposed it to. Sodium sulfate, vanadium oxide, and a highly corrosive sulfur dioxide atmosphere at high temperatures. In less than 2 days, the surface is completely ravaged. I mean, it looks like a lunar landscape, doesn't it? And this brilliantly illustrates why engineers can't just cross their fingers and hope for the best. They absolutely need hard, empirical data. To get that data, we turn to Section 1, the microscopic battleground. Let's zoom right into the metal itself. It's a really common myth that a piece of metal is just one solid, uniform block. As you can clearly see, it's actually a mosaic of microscopic grains tightly packed together. These side-by-side images beautifully illustrate the stark differences in how distinct metal structures react to chemical environments. Depending on the exact alloy and how it was cooled or treated, the shape and size of these grains completely change. And more importantly, the boundaries between these grains, those intricate winding lines you see right there, well, they often become the primary pathways for corrosive attacks. Because corrosion is the ultimate opportunist, it targets very specific localized geometric points within this mosaic. Notice the dark, very isolated areas of attack within this matrix. Corrosion doesn't always just eat away a surface evenly. Sometimes, a single vulnerability at the microscopic level can propagate and eventually compromise an incredibly massive steel beam. Once we locate the damage, we move to Section 2, signs of structural failure. It's time to uncover the actual mechanisms of destruction. Now, this electron micrograph is absolutely fascinating. Let's let our eyes follow the explicit labels here. On the left, you have a solid alpha green. Below it, a healthy, non-altered beta phase. But look closely at the center label, interface. This right here is the active front line of the war. To the right of that jagged line, the healthy beta phase abruptly turns into this damaged, highly porous zone labeled dezinkified beta phase. The metal structure has completely collapsed into a spongy mess. It's wild. So the crucial point is this. What we just saw is a phenomenon known as dezinkification. It's a highly specific form of corrosion where the zinc is selectively leached right out of a brass alloy by its environment. And what gets left behind? Just a weak, porous copper skeleton. Let me be clear, this isn't surface rust you can just scrape off. It's a structural hollowing out that compromises the entire material from within, inviting catastrophic failure, while often looking completely untouched on the outside. Talk about a silent threat. Which brings us to a major question. Section 3, simulating extreme environments. Let's look at how we go about simulating these real-world failures. To truly understand a pipeline, well, you have to recreate one. Here we have a schematic diagram of a dynamic fluid flow loop testing system. I always love showing this because it really highlights the incredible lengths researchers go to in order to interrogate these materials. They literally build these complex closed-loop systems right in the lab to force metals to endure the exact harsh conditions of flowing, heated, pressurized environments. Let's trace how this whole thing builds. Step 1, power and fluid are supplied via the inlet. Step 2, we need total control, so the pressure and flow are perfectly regulated at the metering ball valve and the flow meter. And Step 3, the actual torture chamber. The material sample is trapped inside that heated sample tube, constantly bombarded by corrosive fluid moving at precise velocities, while an ammeter and power control monitor the heat. This setup allows us to fast forward years of wear and tear into mere weeks of lab time. It's like a time machine for corrosion. But dynamic flow loops are really just one piece of the puzzle. Moving to Section 4, tools of the trade. Let's take a look at some of the specialized lab hardware. You know, sometimes the most revealing tests are surprisingly blunt. In the straightforward boiling flask test, we literally suspend raw metallic samples, you can see those two small rectangles hanging in the liquid, directly into boiling chemical baths. We just cook them. It's an aggressive, straightforward way to accelerate natural decay and see exactly how a material stands up to high-temperature liquid environments. But contrast that simple boiling flask with this intense piece of machinery. This is the internal schematic of a high-pressure mechanized loading chamber. When materials are out in the real world, they aren't just sitting in chemicals, right? They're carrying weight. They are under load. Notice the loading shaft at the top, clamping down on those compact-type specimens right in the center. In this chamber, specimens are subjected to extreme mechanical stress, literally being pulled apart, while simultaneously facing high-pressure chemical exposure. This is exactly how we test for stress corrosion cracking. And to gather data from these hostile environments without completely destroying our own measurement equipment, we use these. Here is a varied collection of highly specialized, rigorously calibrated physical testing probes. These are the vital instruments we scientists use to physically reach through the thick steel walls of the pressure chambers and extract precise, standardized data about the electrical and chemical changes happening in real time. Sometimes, though, laboratory simulation just isn't enough. That's when we deploy relentless exposure racks. Entire arrays of stressed specimens are taken out into the real world, to marine environments, industrial exhaust stacks, or even underground soils. Notice how they are bent into tight U-shapes. That bend intentionally introduces permanent stress into the metal. They are just left out there for relentless, long-term environmental exposure testing. We let nature do its worst. All this incredible work leads to one ultimate goal, Section 5, setting the global standard. This is about ensuring real-world safety. Every electron micrograph, every boiling flask, every high-pressure stress test we've looked at today culminates right here in this book. This is the ASTM International Manual for Corrosion Tests and Standards. It's the definitive guide. Engineers and scientists worldwide rely on these exact, rigorously proven methodologies to select the right materials for airplanes, bridges, medical implants, pipelines, you name it. It is literally the compiled knowledge of generations of corrosion detectives, ensuring that the infrastructure all around us doesn't just collapse. So I'm going to leave you with this. Now that you've seen this invisible, microscopic threat up close, the leaching, the grain boundary attacks, the relentless testing required to hold it back, how will this change the way you view the world built around you? Next time you drive over a massive steel suspension bridge or see a network of industrial piping, I want you to remember the silent, microscopic battle being waged inside them every single second, and the dedicated scientists working behind the scenes to keep those materials standing strong. Thanks for joining me on this explainer. Keep asking questions, and I'll catch you on the next one.